In lecture 16, we are going to study the photochemical reactions of metal complex. Metal complex is very important materials for photosynthesis or many photochemical reactions. And this is some way of the understanding, especially for metal complex. So let's go through it. So first, let's remind you that what the metal complex is. It's a kind of general concept. The metal atoms are surrounded by the ligand molecules. So depending on the ligand structure, so this is a tetragonal structure, and this is square type of the structure. And this is probably well-known the octahedral structure of metals, metal complex structure. So depending on the balance of metal and also the property of ligand molecules, there are so many varieties of the electron transfer control and also color control, energy storage, and so on. Many applications. There are many applications by using the metal complex. And especially the reason why the metal complex is so special in the photochemistry is it involves the d orbitals. So d orbitals is, as you see, I skipped these figures, but d orbitals are the sp-d orbital. So the structure is the shape of the molecular orbitals are different. This one is dxy, so it's in the xy plane, but it's clover-like shape. And then YZ and ZX is a similar type of shape, but only the DZ squared is a little bit funny shape like this. So here are what we need to understand when you understand how the light absorption happened in the case of metal complex, and based on the molecular orbital constellation, and it's really it's really relevant to the group theory actually. Okay, so in this drawing, this is the energy level of the metal side. So as you see, since metal has a d, or the electron occupied in a d orbitals, and which has 5 orbitals, as I mentioned, dx, y, yz, zx, x squared minus y squared, and dz squared. And then higher energy level of the s orbital, p orbital, I showed here. The reason is clear later on. And now we also think about the ligand structure, and only we think about a very simple ligand structure with an s orbital. As you see, an octahedral structure. So the simplest one is something like all the s orbitals have the same phase and making this kind of molecular orbital, right? So I would like you to remind that molecular orbitals are made of the linear combination of each of the atomic orbitals. So in this case, we only think about s orbitals, and probably there are many types like this. So this is one side, and then the other side phase difference, but the position are different, and also something different molecular orbitals can be considered. But based on the group theory, we can think about what kind of molecular orbitals are independent, and this is only the result I gave you. So we have 6 orbital and 6 electrons, and 1, 2, 3, 4, 5, 6 molecular orbitals we could find from the group theory. And the other important things I would like to emphasize is for molecular atomic orbital, in this case metal, and a molecular orbital of Riemann field, they can be categorized by the group theory like this. I don't mention how to categorize, but please go back to the group theory study, and then study the general idea. But anyway, it is already categorized in the d orbitals, and three orbitals are categorized into 2T2G, and then 2 of them are categorized into EG, and the s orbital is A1G, and p orbital is T1U. And similarly, these molecular orbitals also are categorized into the each of the groups, the A1G, the T1U, 3A1U. It's actually this one, 3A1U, and these are EG orbitals. Okay. So what we have to do is we have to think about when these two molecular, this metal orbital and ligand orbitals are making another orbitals by making a chemical structure, M plus L. So this is a metal complex. And the important things you have to keep in remember is that only the same type of the orbital can interact to form new molecular orbital, right? So in this case, looking at T2G case, there's no T2G in here. So this molecular orbital is just do not interact with the ligand field. And about the EG case, there's an EG here. So these are, that's why these two and these two are interacting to make bonding and anti-bonding orbitals. So it's shifted toward upwards, right? And similarly, A1G orbital and A1G orbital can be interact to make a bonding and anti-bonding orbital, and T1U could also make the does bonding and anti-bonding. And the most important part in the metal complex is this region, this. So d orbital splitting. This could happen just the T2G stayed in the same energy level, but EG is shifted upward because it's interacting with the ligand field. This energy difference, delta, is close to the visible light region. That's why light is absorbed, so colored, for metal complex molecules. Okay. Here's one of the example. So titanium was so water make a complex of titanium. In this case, this molecule has the shift is about 500 nanometer, which is green. So green light absorbing for this molecules. And also, I'd like to remind you this ligand field was only I consider the s orbital, but of course there are many different types of the atomic orbitals could form the ligand field. So this categorization depend on the which molecular orbital is used, and also the structure. This one is hydro, but a square or some other symmetry case, you have a different type of molecular orbital you could obtain. So it's complicated, meaning that many varieties of the molecules. And also, depending on the here the case when we think about the ligand field using the pi electron medium, the p orbitals is used, and depending on the species, one type of the species a pi electron acceptor, and the other is pi electron donor, and that's also changed the light absorption property of metal complex.